So this video looks at clinopyroxene liquid melt matching. So if you download the folder from GitHub, you can navigate to examples and then click on this Cpx-Liq folder, and then this subfolder, Cpx-Liq melt matching. And then in here there are two examples, Cpx melt match 1, which will be the focus of this video, and this follows the paper of Gleeson 2020 as well as showing a number of other options. And then I'll do a second video showing how we can recreate the results of Scruggs and Paterka 2018. So we can load up this notebook. And I'm just going to quickly show what the input structure looks like. So we can see we've got an Excel spreadsheet from the author's supplement. The first sheet has clinopyroxene compositions, so it has a sample ID, and then all of the oxides along the top with this _CPX afterwards. We also have a tab of whole rock liquid compositions to consider potential matches. Again, we have a sample ID and oxides along the top. And then finally, we have a third sheet, and this is basically from their supplement, and this is the output of the code of DiHd, our paper. So this kind of compares our code to theirs. So first thing you need to do is install Thermobar if you haven't already done it, so uncomment out this line. We're then going to import our various Python things we need. We're going to set our plotting parameters to make pretty plots. And then the first sort of key step is loading in the data. So we're using the import Excel function. The first thing we load are the liquids from this sheet name melts. And we call these liquids, so taking the dictionary out, and it's the lics in it, my liquids. We do a second import for the clinopyroxenes, and the clinopyroxene compositions are stored in this variable. My Cpx is 1. And then finally we use the pandas, so PD, the read Excel function, and this just loads in the entire Excel spreadsheet from Gleeson, which has the results of the R melt matching code. Now, as always, I'm going to encourage you to check your inputs using this display and then myliquids.head and mycpx's.head just to check they read incorrectly. I need to actually run this. And you can see, looking for empty columns, the only empty columns is chromium in the liquid, which we didn't give it, water in the liquid, and potassium in the Cpx. Everything else has been read incorrectly that we would expect. Okay, so if at any point you want help on a function, we just type help pt and then the name of the function. So in this case, we're using the Cpx-Liq pressure temp matching function. Okay, and so we can read down and we can see parameters. We have to give it a data frame of liquid compositions, a data frame of Cpx compositions. So we got those from up here, so that's fine. We've already sorted that. We need to choose an equation for temperature, and these are the options, an equation for pressure, these are the options, or we could also run the calculations at a constant temperature or a constant pressure. And then we can see the defaults up here. So by default, we're using the KD equation for predicting the ideal KD value from Keith Paterka 2008. We're assessing matches within 0.03 for KD, at 0.06 for dark side Hedenbergite, 0.05 for Enstatite ferrocylite, and 0.03 for CATS. And these are from Neve et al. 2019. There are then also options for, so that's all of this. You can set the proportion of iron 3+ in the liquid. You can set a water content, so because, for example, your liquids you've loaded in maybe from XRF don't give a water content, but maybe you have an idea from melt inclusion studies. You could also say Cpx quality is true, and that would filter out clinopyroxenes with cation sums outside this range after David Neve's paper. And then it tells you that it returns a dictionary, and stored within this dictionary are two data frames. The first is AVPTs, which gives you the average pressure and temperature for each clinopyroxene. So, for example, Cpx1 might match liquid 1, 4, 6, and 10. It will average all the pressures and temperatures for those 4 liquids and return one value for that Cpx. Or you can get a data frame of all of your matches. That will give you the match for Cpx1, liquid 1, Cpx1, liquid 4, etc. Okay, so here's how we actually run the function. So we're going to call the output, so the output dictionary, mm1. And we say these are our liquid compositions, these are our Cpx compositions. We want to use equation P from Neve et al. 2017 and equation 33 for temperature from Peterka 2008. And we want to run our calculations with a water content of 0.5. And then we want to extract the two data frames. So mm1 all, this is every single match, and mm1 average, this is the average matches. So we can run this. We can see it just prints some intermediate things just so you know what it's doing, and this can be really helpful if you've given it like thousands or tens of thousands of liquids to match to. So first of all, it's telling you the total number of pairs it's assessing. So 12,714 pairs. And then it's told you how many matches remain after an initial KD filter. And we basically built this in to help speed up the code. So what it does is, the problem with assessing KD matches is that you need to know the temperature using equation 35 of Peterka. But obviously we don't know the temperature because we're iterating towards the temperature. So one solution would be to take all 12,000 liquid Cpx pairs and iteratively calculate pressure and temperature for these, and then remove those which don't pass the equilibrium filter. However, you can see if you have 300,000 matches, this is going to be very computationally inefficient. So what we said is, okay, we don't know the pressure, but we can probably guess a reasonable range of pressures. And by default, the code sets a minimum pressure as -20 kilobar and a maximum pressure as 30 kilobar, and you can adjust this maximum pressure. So what it does is it calculates the temperature for that minimum pressure, and it calculates the temperature for the maximum pressure. And then it calculates the KD value for those two sort of extremes of temperature. And if you aren't a match, if any given Cpx liquid pair isn't a match to either of those, it's not going to be a match at any temperatures in between as well. So we can throw out all of those pairs which don't match at those pressure extremes. And in this case, this allowed us to throw out like 9,000 Cpx liquid pairs. So then for the remaining 3,800 pairs, it goes through and it iterates pressure and temperature, and then it applies an additional KD filter. And then because it now has pressure and temperature, which is needed for the other equilibrium tests, it goes through and it checks CATS, dioxide Hedenbergite, and N-type ferrosilicate. And then the final thing it does so it says finishing calculating P's and T's, and then finally it averages the results. So it takes all of the liquids which match a given Cpx and averages those. And then it tells you it's done. So we can look at the average output. What we can see is the sample ID of the Cpx, so only 3 Cpx's matched any liquid, Cpx-64, Cpx-65 and Cpx-66. This is the mean temperature calculated for those matches for Cpx-64, the standard deviation of the temperature, the mean pressure, the standard deviation of the pressure, and then you've got the values of various equilibrium tests here. And you can keep scrolling along, and then there's various stuff there which might be useful. Now, you can also look at what the all looks like. So you can see that Cpx-64 matches quite a few. Cpx-65 doesn't match any really, well, like a handful, and 66 only matches 2. Okay, so say you think you know your temperature from another proxy, so you don't want to do this iteration. That's fine. We're going to do the same. We're just going to call it mm1 fixed T this time. And instead of having an equation T, we just have T equals 1450. And we can have a look. And the first 5 rows are all of the matches to Cpx-64. We can get rid of the head and look at generally. And we see that actually almost all of our matches are to 64, and only 1 match to 65 and 1 match to 66. Similarly, we can run the calculation at a fixed pressure. So here we specify an equation T, and P is an integer, so 5 kilobars here. And we can run that. Okay, so when we use that initial iteration between pressure and temperature, we really only got 3 Cpx's that were matching liquids. So Gleeson et al., what they decided to do was to increase sort of the path filters for when to take equilibrium pairs. This is very reasonable given that we know that these filters are 1 sigma values, so it's quite probable that some of them will lie within 2 sigma. So instead of the default Cats of 0.03, we double it to 0.06, diopsid Hedenbergite double to 0.12, and N-type ferrocylite double to 0.1. And we keep the KD filter the same and the water content the same. And we're going to call these output MM1 and then 2S to show that we've doubled the 1 sigma values for these 3 equilibrium tests. Then we can look and we see, if we look at the averages, we now have a lot more CPXs passing. Almost all of them have a match to a liquid. Okay, so previously what we've been doing is we've been using that KD ideal value from Paterka, which is a function of temperature. We might instead want to use a fixed value of KD. So here we're setting this by saying KD match is 0.27. And instead of using that 0.03 pass filter, we're going to increase it to 0.08, which is the 1 sigma value that Paterka suggested. Finally, we're going to set the proportion of Fe3+ at 0.15, and we're going to leave these equilibrium filters the same. So we can run this. Okay, so those filters are sort of ideal for sort of tholytic, traditional volcanics. What Masotta showed is that KD filter in particular doesn't do a very good job for alkaline rocks. So they have their own parameterization for KD, and we can choose to use this by saying KD match equals Masotta. And here as well, we're choosing an equation pressure from that study and an equation temperature. So this would be if you're working in an alkaline system. It's probably not applicable to this Galapagos example. I just wanted to show it to show how you would customize the function. And then everything else is the same here. So what it says is, caution, you have selected the KD FEMG model of Masotta. This is only valid for trachytic and phonolytic magmas. You should be using Paterka KD if you're outside of those. And then it's just going through, and it's actually telling you you've selected a pressure independent function for temperature. So actually it isn't iterating pressure and temperature, it's just solving them on their own, and the same for these. Okay, and you can look at the matches. And then just in contrast to that, the default is KD match Paterka, but if you want to be able to keep track in your script, you can type that out just so you remember. And let's say we only want to consider a filter based on KD. We don't want to use the Cats, the diopsid Hedenbergite, and the N-type ferrocylite. The easiest way to do this is to set the errors for these path filters very high. So here we've set them to 10. So this is really only applying that KD filter from Paterka. Okay, and then we can look at the results from these various equilibrium filters. So we're going to compare the first 2 things we ran. So the first one is that melt match 1, and that was using the default filters. And the second one is this melt match 2S, where we increase the pass rate for N-type ferrocylite, diopsid Hedenbergite, and Cats. So we're plotting this as a subplot with 4 different axes. On the first axis, we're going to plot the delta KD value for Paterka. This just sets up the weighting so that the histograms are the same height even for different numbers of matches. Second axis, we're going to plot the N-type ferrocylite value from Mollo 2013, diopsid Hedenbergite from Mollo 2013, and the Cats, and this is based on Paterka 1999. So what you can see is the delta KD values all stop at 0.03 because that was the filter we used for that. The N-type ferrocylite for the first one stops at 0.05, and the second one stops at 0.01. Diopsid Hedenbergite, the same, you basically double number of matches. You've got all of these which were discarded the first time but aren't the second time. And same for Cats, you suddenly are taking all of these matches here. We can also plot the pressures and temperatures that we get out. So here we're going to again compare the results where we use 1 sigma and where we use 2 sigma. So on the first axis, AX1, we're plotting all of the temperatures that we calculated, and we're taking 273.15, so we get them in Celsius, against all of the pressures, and we're plotting this as a light cyan dot with a transparency of 0.5. We're then going to plot an error bar, and this is using the average, the mean, so this is averaging per Cpx, and we're also going to do the average for the pressure, and then the x error is the standard deviation of those Cpx's, and the same for the y error. And then we're going to do the same thing for those two S matches. So we can run this. So what you can see, as we already knew, for the 1 sigma matches, we only have 3 Cpx's, which are shown as these error bars, and then all of the individual matches for those Cpx's are shown here. And then once we increase that to 2 sigma, we end up with a lot more Cpx's, where each diamond is an individual Cpx, and all of the individual matches are underlain underneath in these red points. So we can compare the results from this code to the published data from Gleeson, and we're going to show the average matches because that's what they use in their study. So we're going to plot again these error bars, and then plot these against this data frame we loaded in at the start called published, and their temperature and pressure columns. So from Thermobar, you can see all the cyan matches, and then from the Neve code, you can see the yellow stars. And in general, these are very, very similar. The difference being that Neve's code returns 2 distinct clusters. Now, the reasons for this are several. The codes work in different ways. So how David's code works is it iterates towards a solution and is throwing out matches along the way. But it might be that some of those matches that were thrown out on the way, by the time you've converged to the final pressure and temperature, actually end up being a match. So that could explain why we get a lot more matches using this Python code. The second thing that's different, I don't have access to the code, but it seems from the spreadsheets that it is using, when it calculates KD, it is using the temperature from the 1999 Peterka equation. Whereas my code is using the temperature that you specify in the equation T. So there is a difference in the KD filter being used there. We use the temperature the user specifies, the equation they want to use, to be consistent, rather than basically iterating with 2 separate temperatures. But in general, we can see in terms of our interpretation of this volcanic system, the codes give identical results. Storage is predominantly between about 5.5 and 10 kilobars.